Hey everybody, welcome back to Trigonometry. Today we're in section 4.1 and we're going to be switching gears and learning about graphs of the sine and cosine functions. So in this section we will talk about what a periodic function is. We'll learn how to graph the basic sine function and the basic cosine function, and then we'll talk about how to graph transformations of those graphs that involve amplitude and period. And then we'll also look at a few graphs and learn how to determine the equation that produced that graph. So let's get started. So first of all, what is a periodic function? Well, a periodic function is one that repeats. Each repetition of a periodic function is called a period or a cycle. And you can see that the graph we have here is a periodic graph because it repeats the same pattern at a regular interval. Now the length along the horizontal axis from the beginning of one cycle to the beginning of the next cycle is also called the period. With all periodic functions, each cycle covers the same distance on the horizontal axis. In other words, the period is the same for the whole graph. So if it takes, for example, 4 units to get from this peak to this one, it will also take 4 units to get from this peak to the next one and from this peak to the next one. So here we are in example 1, and it says determine the period of each periodic graph. So if we look at the graph in part A, we know that this is a periodic graph because the same pattern repeats at a regular interval. So we could say that right here is one period of the graph because it goes from the beginning of the pattern to the beginning of the next pattern. And if the first pattern starts here at x equals 0 and the second pattern starts at x equals 4, then 4 minus 0 is 4, and that means the period for this graph is 4. And you can see that the period is the same for every cycle on the graph. So the second cycle goes from 4 to 8. It still covers 4 units. The next pattern goes from 8 to 12. That's still a difference of 4 units. And so like we noticed before, the period should be the same for every cycle on the graph. And now let's look at the graph in part B. So you can see that the pattern here goes like this. And so how many repetitions do we have? 1, 2, 3, 4 repetitions of the pattern means we have 4 cycles here. And so this first cycle, or this first period of the graph, starts at the axis and goes to right here. And we don't have a label on the horizontal axis right here. So let's see if we can figure this out. If from here to here is 50, then this mark right in between must be 25. And if here to here goes from 50 to 100, then this mark right here must be 75. And so from the axis to this point right here is 75 units. And so we can say that the period for this graph is 75. And if that's true, it should be 75 units from here to here. And it is. 150 minus 75 would also be 75. And then 75 units from here to here, and that holds up as well. So the period for this graph is 75. Now here are the graphs of a couple of functions that are not periodic. This one is oscillating back and forth, but it's not periodic because we don't have the same pattern repeating exactly at a certain interval. The pattern is, it looks sort of the same, but it's growing, so it's not really the same. So this is not considered periodic, and neither is this. Although we have the same shape repeated, it's not repeated at the same interval. You can see here we have a spike, and then 2 smaller crests, and then we have another spike, and 2 crests that are not the same as the first 2, and then we have another spike, and lots of crests, more than 2. And so this is not the same pattern at all. This is not periodic. Now the graphs of the trig functions are considered periodic because they repeat as theta increases. In other words, imagine an angle here, and imagine that the terminal side of this angle is traveling around the circle. What we're going to see is that as that terminal side travels around the circle, the graphs that the trig functions produce repeat and create a periodic graph. So let's see if we can generate a graph of the sine function. Now I want you to remember that the sine of theta is equal to the y-coordinate of any xy point on the unit circle. So we're going to be imagining an angle here on this unit circle, and we're going to be tracking what happens to the y-coordinate as that terminal side travels around the circle. And you can see that as long as we're looking at a point on the unit circle, the highest y value that we're ever going to get is 1, and the lowest y value that we're ever going to get is -1. So the sine of theta will always be between +1 and -1. And now let's make some tick marks on our horizontal axis. So this first tick mark represents when the terminal side is at 0 degrees. And then I'm going to put 1 tick mark for every 90 degrees, or 1 tick mark for every pi/2 radians, because we will typically label our horizontal axis in radians. So 1 tick mark for pi/2 radians, another tick mark for pi radians, then 3 pi/2, and then 2 pi. And I'm going to make this last one bigger because that's the end of our first trip around the unit circle, or in other words, it's the end of our first period. Now let's go back and label these tick marks. We won't do this every time, but we'll do it this time. So this first tick mark represents when the terminal side is at pi/2. The second tick mark represents when it's at pi. The third tick mark represents when it's at 3 pi/2. And the fourth tick mark represents 2 pi. Now, let's think about what happens to the y-coordinate as that terminal side makes that trip around the unit circle. So, looking at the y-coordinate. So, when the terminal side is sitting at 0 radians, the xy coordinate on the unit circle is 1, 0. So, the sine here is 0. So, I'm going to put a dot at 0 on that tick mark. And then imagine that the terminal side travels to where it's pointing straight up. So the terminal side of our imaginary angle is going through 0, 1. So when the angle theta is pi/2 radians, the sine of that angle is 1. And so on my graph, when the angle is pi/2 radians, I'll put a dot at 1 because the sine there is 1. Okay, now imagine that the terminal side of our angle travels to here. So it's going through the point -1, 0. Now the sine value of this angle is 0 because our y-coordinate is back to 0 here. So when the angle is pi radians, the sine of that angle is 0. Then as the terminal side of our angle goes from pi radians to 3 pi/2 radians, we see that the sine value changes from 0 to -1. So we're going to put a dot here at -1 for 3 pi/2 radians. And then as that terminal side goes from 3 pi/2 to 2 pi radians, the sine value goes from -1 to 0. And so we're going to have a 0 here at 2 pi radians. And now this is not the graph, but this is just the outline of our graph. To complete the graph, we need to connect the dots. So let's think about what happens to the y-coordinate here on the circle. You can see that the y value is changing quickly at first, and then it kind of levels off. And so we're going to see the same thing reflected on our graph here. The graph is going to go almost straight up at first, and then it's going to level off as we reach that next point, like this. And so it kind of looks like a hilltop. And the same thing happens as the sine value goes from 1 back to 0. We kind of have that hilltop effect. So you can see like that, it's kind of rounded. So now look, it's not a semicircle, and it's definitely not pointed, but it's kind of a hilltop. The same thing happens as the terminal side goes from 0 down to -1, and then from -1 back to 0. So you'll see it kind of make like a valley shape here at the bottom, almost a U shape. And so we get what I call hilltops and valleys here. Now let's imagine that we let the terminal side of our angle continue around the unit circle for a second trip. So that would produce a second pattern here on our graph. let's go ahead and draw ourselves 4 more tick marks. So our terminal side right now is here. If we go around the circle again, we'll have 1, 2, 3, 4 more tick marks, and again for the 4th tick mark we are back at our starting position, so I've made that one larger. Now let's label these. So if we were already at 2 pi radians, you know 2 pi is the same as 4 pi over 2. So if we're already at 2 pi or 4 pi over 2 radians, well then traveling another pi over 2 would put us at 5 pi over 2 radians. And then traveling another pi over 2 would put us at 6 pi over 2, which simplifies to 3 pi radians. Okay, now add another pi over 2. 6 pi over 2 plus another pi over 2 puts us at 7 pi over 2. And then add another pi over 2, and we're back at 8 pi over 2, which simplifies to 4 pi. Now it makes perfect sense that this last label is 4 pi, because we know that it took 2 pi radians to get from 0 to the end of the cycle. So it should take 2 pi radians to get from here to the end of the next cycle. 2 pi plus another 2 pi should put us at 4 pi at the end of that second rotation around the coordinate system. So let's see what happens as we go again. So we were already here. That's represented by this dot right here. So when we travel again to 5 pi over 2, the sign value is 1. Then at 3 pi, the sign value is 0. Then at 7 pi over 2, we're back to negative 1. At 4 pi, we're back to 0. And so we would then connect these dots the same as we connected the dots for the first pattern. And so we'll want to have the graph go up, kind of level off at the top, and then come down with that hilltop kind of shape. And then as we finish the last half of this period, we want to let the graph come gently down to negative 1 and then curve back up to 0. So again, notice the hilltops and valleys. Hilltops and valleys. Now we'll want to remember the basic shape of this graph, and what that really means is just remembering how the dots are laid out. So I'm going to say that we have like a low, middle, and high position for our dots. So we can see that the sine function starts in the middle. So I'm going to say that the basic shape here is middle, high, middle, low, middle. And you can see that's exactly what happened for the second cycle. It started in the middle, and then it went high, middle, low, middle. And every time the terminal side of our angle travels around the coordinate system again, the sine function will produce another repetition of this pattern. Now let's talk about the domain. So as you probably remember from algebra, the domain of a function is all of the values that can be plugged into it. So here where we're talking about the sine of theta, the domain is every angle that can be plugged into the sine function. And that's every angle from negative infinity to positive infinity. So the domain of the sine function is negative infinity to positive infinity. The range of a function is all of the y values that can come out of that function. And you can see here that the lowest y value that the sine function can reach is negative 1, and the biggest y value is positive 1. So the range here is negative 1 to positive 1. As you know, the period is how many radians it takes to complete a whole pattern. And we know that the terminal side of our angle had to travel all the way around the circle, so 2 pi radians, in order to complete the pattern. And you can see it on the graph here as well. The pattern starts at 0 and ends at 2 pi. So that covers a length of 2 pi radians. Or we could also look at this second one. It starts at 2 pi and ends at 4 pi. That's a difference of 2 pi as well. So we know that the period of the sine function is 2 pi. The x-intercepts are where the graph is crossing the horizontal axis. So if you look at what we've got right here, we can see it's crossing at 0, 1 pi, 2 pi, 3 pi, 4 pi. If you had to say in words what the x-intercepts are, you would probably say it's crossing the horizontal axis at every whole multiple of pi. But when we write things in math notation, we need to generalize it into more of a formula. So we would say that a formula for calculating the location of the x-intercepts is n pi, where n is any integer. And you can see that no matter what integer somebody plugged in here in this little formula, it would allow them to calculate the location of another x-intercept. Now you're going to be graphing sine and cosine functions on your own later, so here are some tips for how to do that well. The tick marks on your horizontal axis should be as evenly spaced as possible. One starting tick mark, like you saw me do on the last slide, and then 4 tick marks for each period that you're graphing. The highest and lowest points of the graph should be labeled on the vertical axis, and the end of each period should be labeled on the horizontal axis. So for my class, I'm not going to ask you to label the intermediate tick marks, just the first one and the last one for each period. Your graph should be smooth. It should look like hilltops and valleys like we saw before. It should not be pointy, and it should not look like semicircles. And for the basic graph, which is all we've done so far, the first point in the pattern must touch the y-axis. In other words, the first point should occur at x equals 0. It is possible to have a function where the first point is not at x equals 0, but we'll talk about that in the next section. As long as you're graphing just a basic sine or cosine graph, the first point in your pattern should be on the y-axis. Okay, so let's practice from scratch drawing 2 periods of y equals sine theta. And we'll do it the way we did before, only we won't label every tick mark on the horizontal axis. So notice it says label the highest and lowest points on the vertical axis and the end of each period on the horizontal axis. Okay, I'm going to mark my vertical axis first, so we know that the highest and lowest points for the sine of theta are +1 and -1. And notice that I've got them as evenly spaced as I can. So I don't want one much closer to the horizontal axis than the other. They should be about the same distance away. And then for the marks on the horizontal axis, the first one goes at the origin, and then I need 4 more for each period that I want to draw. I want to do 2 periods. So I'm going to go 1, 2, 3, 4, and notice that 4th one is larger than the others because that's a visual reminder to me that this is the end of the first cycle and the beginning of the next cycle. And then the tick marks for our second cycle, we're going to go 1, 2, 3, 4, and again that last tick mark is larger because that represents the end of the second cycle. And then let's put a label on the end of each cycle here. So we know that the period of this function is 2 pi, so from 0 to here should be 2 pi, and that means the label here is 2 pi. And then from here to here is another 2 pi, so 2 pi, which is where we're starting from, plus another 2 pi is going to make 4 pi. And those are the labels for the end of each period. And now let's remember that the pattern for sine of theta was middle, high, middle, low, middle. So we'll put our dots in first. Middle, high, middle, low, middle. And then go ahead and add the dots for the next pattern. We're already at middle, so then the next thing is high, middle, low, middle. So let's look at it. Middle, high, middle, low, middle. So this point is both the end of the first cycle and the beginning of the next cycle. So for the second cycle, middle, high, middle, low, middle. And then let's connect the dots the way we know we're supposed to. Remember, we don't connect them with pointy straight lines. We don't connect them with semicircles. We create those hilltops and valleys. Just like that. And there we have 2 whole periods of y equals sine of theta. Now let's do the same thing for the cosine function. Now this time, since we're graphing cosine, we'll be concentrating on the x-coordinates of the points on the unit circle. But we'll still set up our graph the same way. So we want to label our y-axis with the lowest cosine value and the highest cosine value. And remember, we're concentrating on x-coordinates over here. So the smallest x-coordinate on the unit circle is this -1, and the largest x-coordinate on the unit circle is this +1. So on our vertical axis here, which represents our cosine values, we will still have -1 and +1. Now, for the horizontal axis, we want a tick mark for each quadrantal angle. And so we know that the first one occurs at 0 radians, and so it goes at the origin right there. And then the next 4 tick marks will represent pi/2, pi, 3 pi/2, and then 2 pi. So I'm going to put 1, 2, 3, 4 tick marks, and that fourth one, because it represents 2 pi, I've made it a little longer than the others, so it's recognizable as the end of the period. Okay, I'll go ahead and label that one 2 pi. And then to graph a second period of the cosine function, I need 4 more tick marks. So 1, 2, 3, 4. This second one is 2 pi more than the last one. The label at the end of the second period is 2 pi more than the label at the end of the first period. So 2 pi plus 2 pi is 4 pi, and that's the label that goes there. Now, let's start here, and at each quadrant, we will put a dot on our graph to represent the cosine value. So at 0 radians, the cosine value is 1. See that right there? At 0 radians, the cosine value is 1. And then, as the angle grows to pi/2, so that the terminal side is pointing straight up, the cosine value goes to 0. So right here, the cosine value is 0. Now the next tick mark is for pi radians, and at pi radians, the x-coordinate on the unit circle is -1. So that means the cosine value is -1. And then, as the terminal side continues on around, we come to 3 pi/2, so the terminal side would be pointing straight down, and the cosine value there would be 0. And then the terminal side continues on around until it reaches 2 pi radians, where the cosine value will again be 1. Okay, so now we've got a whole period of the cosine function, and before we place the dots for a second period, let's go ahead and connect these dots. So let's look at our unit circle, and again, I want you to think about how the x-coordinate is changing as we go from x equals 1 to x equals 0. It looks like it's not changing very fast at first. Notice the x value does not change a lot here, but then once we get about halfway, the x value begins to change really quickly, so that we get that roundness at the top of the circle. And that's going to show up when we connect our dots. So at first, the x value is not changing very quickly, so the graph will be a little flat, and then it will drop almost straight down to this 0 point. And that's going to look like that. It's exactly the same shape that we saw with our hilltops and valleys with the sine function. Okay, now as we go from 0 to -1, the same thing. The x value drops off pretty fast, and then as we get close to -1, it kind of flattens out. And so that's what we're going to see here. It drops really fast until we get close to -1, and then it flattens out, just like that. That's that valley shape. And then it continues the same as we did with the sine function. So we're going to have that little roundness at the bottom, and then go straight up to the middle, and then go straight until you get near the top, and then round off. It's the same shape that we had for the sine of theta, but everything's just been moved over. Now let's get the dots for our second rotation around the unit circle. So right now, our terminal side is at 2 pi, so it's right here. And as the terminal side grows to 5 pi/2, the cosine value goes to 0, Remember, that's that x-coordinate there. And then as we continue on around the coordinate system, the x value will go to -1, then it will go back to 0, and then it will go back to +1. And so we will connect these dots the same way we connected the first set. So gently sloping down, and then making that kind of valley shape at the bottom, and then gently sloping up to the high point. And right here you have two complete periods of y equals cosine theta. And let's get our basic shape recorded. So the basic shape for the cosine function is high, middle, low, middle, high. And you can see that when we do the second pattern, it follows the same basic shape. It starts high, so that's where the first cycle ends is where the second cycle begins. So it starts high, and then it goes middle, low, middle, high. Okay, domain, we know, is any number that can be plugged into the cosine function, and every angle has a cosine, so the domain here is -infinity to +infinity. For range, that's the lowest y value to the highest y value. And so our range goes from -1 to +1. The period, again, is the number of radians it takes to complete a whole pattern. We have to go all the way around the circle to get a whole pattern, so that's 2 pi radians. You can also see it here on the graph because you know that 2 pi minus 0 is 2 pi radians, or you could also say 4 pi minus 2 pi is 2 pi radians. So the period is definitely 2 pi radians. The x-intercepts are a little more complicated than the x-intercepts for the sine function, because you might remember that with the sine function, the x-intercepts were occurring at every n pi, in other words, every whole pi. But here, the whole pi's do not have x-intercepts. In other words, the graph does not cross the horizontal axis at these whole multiples of pi. Where is it crossing? Right here. Well, we don't have labels on these, but we could have. Remember, this would be pi over 2. This would be 1 pi. So this would be 2 pi over 2. So this next one would be 3 pi over 2. Then we've got 4 pi over 2. Then 5 pi over 2. Then 6 pi over 2, which is 3 pi. And then 7 pi over 2. And so where do you think the x-intercepts are occurring? It's tempting to say that the x-intercepts are occurring at every half pi, but that's not quite accurate, because technically speaking, these whole multiples of pi are also half multiples of pi. This is 2 pi over 2. This is 4 pi over 2. So we don't want to say that the x-intercepts are occurring at every half pi. Instead, think about the pattern we're getting here. The x-intercepts are occurring at 1 pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And the next one, if we were to draw it, would be at 9 pi over 2. So do you see the pattern? The x-intercepts are occurring at every odd pi over 2. So if we wanted to write it in words, we would just write that the x-intercepts are happening at the odd pi over 2's. But we want to write it in math notation. So the way to express an odd number in math notation is this way. We'll say 2n plus 1 times pi over 2. And the reason this works is that n is going to be any integer, right? So n is like +1, +2, +3, or it could be -1, -2, -3, and so on. If you take an integer, whether it's positive or negative, if you take an integer and you multiply it by 2, now you have an even number. So if n is an integer, then 2n is guaranteed to be an even number. And then if you add 1 to that, well, then that's guaranteed to be an odd number. So 2n plus 1 is just the mathematical way of expressing any odd integer. Okay, and so we want the odd pi over 2's. So a formula for calculating all the x-intercepts here would be 2n plus 1, because that's going to make an odd integer, times pi over 2. Now let's take just a second to compare our sine function, which I have here on the left, with our cosine function, which I have here on the right. We remember that the sine pattern was middle, high, middle, low, middle. And now we know that the cosine pattern is high, middle, low, middle, high. So it looks like the cosine function is just as if somebody had taken the sine function and scooted everything over pi over 2 radians. If you could move this point over pi over 2 radians to the left, then it would look just like the cosine function. And the same thing here. If you could take this point and move it pi over 2 radians to the left, well, then you would get the second point of the cosine function. And the same pattern holds true all the way across. So the graph of y equals cosine theta is actually the same graph as y equals sine of theta, but everything has been shifted pi over 2 radians to the left. And now let's practice drawing 2 periods of the graph of y equals cosine theta. Again, label the highest and lowest points on the vertical axis and label the end of each period on the horizontal axis. So we know that for the cosine function, the highest y value is 1 and the lowest y value is -1. And then we know that for the horizontal axis, we want to make one starting tick mark at the origin, and then we want to go 1, 2, 3, 4, and that will be the end of the first period. And then for the second period, we go 1, 2, 3, 4, and that's the end of the second period. Now, to label our horizontal axis, all that's necessary is that we label the end of each period. So if we start at 0 and we move out one period, which is 2 pi, then we will be at 2 pi radians. And from there, if we move out another 2 pi, we'll be at 4 pi radians. So from the beginning of the first period to the end of the first period is 2 pi radians, and from the beginning of the second period to the end of the second period is also 2 pi radians. Okay, now let's put our dots. We know that the pattern for the cosine of theta is high, middle, low, middle, high. And then repeat that. We're already at high, so then go middle, low, middle, high. And then we want to connect the dots. Remember, it's not pointy and it's not semicircles, but it's hilltops and valleys. So right here, we're at the top of a hilltop, so we're going to gently slide down to the horizontal axis and then slide down to the lowest point and then kind of, flatten it out there at the bottom. And then come back up the same way and then repeat that. Gently down and gently back up. And there we have 2 periods of the graph of y equals cosine theta. Now that we've got the basic graphs for y equals sine of theta and y equals cosine of theta, let's learn how to do transformations on these graphs. And in order to do that, we need to talk about something called amplitude. So amplitude is the height of the graph from the center to the top. Or you could also do it from the center to the bottom. Either way is fine, but it's probably easiest to think about going from the center to the top. Now, the number that controls your amplitude is going to appear as a multiplier in front of your sine function. So in the function y equals a sine of x, the number in the a position determines the amplitude. Amplitude is the absolute value of whatever number you have in the a position. So amplitude is always positive even if a itself is negative. Now in this graph, you can see that we have the graph of y equals sine of x in this dotted form right here. And then if we wanted to graph the function 4 times the sine of x, we would just multiply 4 times each of the original values from y equals sine of x. Now the easiest values to multiply by 4 are the 1s and the -1s and the 0s. The others we'll just trust to naturally follow the pattern. Okay, so right here, where the sine of x has a value of 0, 4 times the sine of x also has a value of 0, because 0 times 4 is still 0. Right here, where sine of x has a value of 1, 4 sine of x has a value of 4, because 1 times 4 is 4. And then again, where sine of x is equal to 0, 4 sine of x is also equal to 0. Where sine of x is -1, 4 sine of x is -4. And then back to 0. So you can see that 4 sine of x looks exactly like sine of x, except it's been stretched vertically. Everything's more exaggerated. But notice that the x-intercepts did not change. So a number in the A position changes the amplitude. In other words, it changes how tall the graph gets, but it does not change the period because the x-intercepts did not change. Okay, here's example 2. And it says the graph below shows 2 periods of y equals sine x. Graph 2 periods of y equals 3 sine x on the same coordinate system. So all we're going to do is what we saw on the last slide. We'll just multiply every value by 3. Here, where sine of x is 0, 3 times 0 will still be 0. But here, where sine of x is 1, 3 times 1 will be 3. And then where sine of x is 0, 3 sine of x is also 0. Where sine of x is -1, 3 times -1 is -3. And then we can continue that pattern all the way across the whole 2 periods. And now let's connect the dots. We connect the dots the same way, only the hilltop will be steeper. So it will look sort of like that. And that is a sketch of 2 periods of the graph of 3 sine x. So basically, we can think of the graph of a sine theta as a vertical stretching of the graph of y equals sine theta when the absolute value of a is greater than 1. So we know that when a is, say, for example, 2 or 3 or 4, it's just going to vertically stretch that original graph of y equals sine theta. And a sine of theta will be like a vertical shrinking of the original graph when the absolute value of a is less than 1. In other words, when a is a fraction, a proper fraction like 1/2 or 2/3, the graph will actually shrink instead of being stretched. And the same thing goes for cosine. It works the same for both functions. And now that we know what a change in amplitude does to the graph, we can draw the graph of a sine of x or a cosine of x directly without having to draw the original graph first. So let's get an example of that here. This is example 3, and it says graph 2 periods of y equals 2 cosine x. Be sure to label the highest and lowest points on the y-axis and the end of each cycle on the x-axis. Okay, so let's think vertical axis first. We know that cosine of x would normally have y values that go from -1 to +1, but now everything's being multiplied by 2. So everything's going to go from -2 to +2. So our lowest point will be -2 and our highest point will be +2. Now for the horizontal axis, we do it the same as we did before. We start at the origin and then we lay out 4 tick marks, 1, 2, 3, 4. And that's the end of the first period, so that will be 2 pi. And then to get a second period, we'll go 1, 2, 3, 4. And that will be the end of the second period. So 2 pi plus 2 pi gives us 4 pi. Okay, now the pattern for cosine of x, you remember, was high, middle, low, middle, high. So our dots are going to go high, middle, low, middle, high. And then we repeat that. We're already at high. So high, middle, low, middle, high. And there we have the outline of 2 periods of 2 cosine x, but we need to connect the dots for it to be complete. So again, think hilltops and valleys. So starting high, we're not going to go straight down because remember it's like a hilltop. It goes out a little bit before it starts going down. So gently down, then gently back up. And when you've connected all your dots, then you have 2 complete periods of the graph of 2 cosine x. Now, we said that amplitude was the absolute value of a. So what happens if a is negative? Well, if a is negative, in other words, if a is less than 0, then the graph will undergo a reflection about the x-axis. and I'll just say flip for short instead of saying reflection about the x-axis every time. It's just going to flip vertically. And if you think about it, that makes sense, because if you take every y value from the original graph and multiply it by a negative number, it will change the sign of every y value. So what was above the x-axis will now be below it, and what was below will now be above. In other words, it flips it over. So here we have example 4, and it says graph 2 periods of y equals -2 sine x. Label the highest and lowest points on the y-axis and the end of each cycle on the x-axis. Okay, so again, we know that the amplitude is 2 here because a is -2, so the amplitude is the absolute value of that. So our amplitude is 2. We'll need to have that labeled on our vertical axis. And then, because we want 2 periods, we're going to put our tick mark at the origin, and then we're going to go 1, 2, 3, 4. That's the end of the first period, so that's going to be 2 pi. And then 1, 2, 3, 4. And here's the end of the second period, so that's 4 pi. Now we want to remember the pattern for sine of x. The pattern for the original basic sine of x function was middle, high, middle, low, middle. But this one needs to be flipped upside down because of the negative here. So our dots are actually going to go middle, low, middle, high, middle. And that is the outline of the first period. And then we'll just continue the pattern. So we're already at middle. So again, it goes middle, low, middle, high, middle. And now to complete the graph, we just connect the dots. So remember, hilltops and valleys. So first we're going down. And don't go straight down so that your graph comes to a point, but slope down so that you gently come to that second dot. So it's going to look like that. And then round the bottom and come back up. And then continue the pattern until you've finished the second period. Now let's move on to a different type of transformation. Let's talk about how to change the period of a sine or cosine function. So just a reminder, the period is the distance along the horizontal axis from the beginning of one cycle to the beginning of the next cycle. So in the graph of y equals sine of bx, a number in the b position will affect the period. In the graphs of y equals sine of x and y equals cosine of x that we've been graphing, we have always had b equal to 1. So we have already seen that when b equals 1, the period equals 2 pi. Now, the larger the absolute value of b is, the faster the graph will go compared to the original function where b was 1. And the smaller the absolute value of b is, the slower the graph will go in comparison to the original function. Now, in order to be technically correct, we've had to put b in absolute value bars here. That's because it's possible for b to be negative. However, in this course, we will only ever deal with positive b values. So here's the formula for the period. The period is 2 pi divided by whatever number is in the b position. So we'll just say 2 pi over b, and that's how you calculate period. Notice that since b is in the denominator, it makes sense that as b gets larger, the overall fraction and therefore the period gets smaller. So given what we just saw in the last slide, we can think of the graph of y equals sine of bx as a horizontal shrinking of the graph of y equals sine of x whenever the absolute value of b is greater than 1, and it will be a horizontal stretching of the original sine of x graph when the absolute value of b is less than 1. And the same thing goes for cosine, of course. Okay, look at these two graphs right here, and you can see what I'm talking about. Here we have y equals the sine of 2x, and look how the graph moves faster than our original sine of x graph, right? Because the original sine of x would have only completed one period between 0 and 2 pi. But here we see this one completes 2 periods between 0 and 2 pi. So that's what I mean when I say it moves faster. On the other hand, here's the graph of y equals sine of 1/2 x, and you can see that it moves slower compared to the graph of y equals sine x. So it only can fit half of a period between 0 and 2 pi. And so that's why we say if the absolute value of b is greater than 1, like we have in this first graph, it horizontally shrinks the graph. But if the absolute value of b is less than 1, so it's like a fraction, then that horizontally stretches the graph. So here's how we're going to handle graphing y equals sine of bx or y equals cosine of bx. So first you'll divide your x-axis into 4 equal parts. That means you will draw a starting tick mark plus 4 more tick marks. And for right now, our starting mark is always at the origin. That will change in section 4.2, but for right now, the starting mark always goes at the origin. And you will always want to label the last tick mark of each period. And the way to calculate the label is to take the starting position plus the period, and that gives you the ending position, and that's the label that will go on that tick mark. Now, one cycle or one period of the graph will fit on those 5 marks, and you'll use the basic shape to plot the 5 points on those 5 tick marks. And then if you need to draw a second cycle, which you usually do, then you'll draw 4 more tick marks and repeat the process. And the horizontal axis label for the next cycle is always found by adding the starting position plus the period, just like we did up here. So let's practice with that. This is example 5, and it says graph 2 periods of y equals sine of 3x. Label the highest and lowest points on the y-axis and the end of each cycle on the x-axis. Okay, so let's analyze a little bit. Here we see that the number in the b position is 3. So b equals 3, and that means period is 2 pi over b, so that's 2 pi over 3. Now the number in the a position is a 1. It's invisible here. We did not have to write it, but we know that when there's no coefficient, the coefficient is a 1. So amplitude is 1. That lets us label our vertical axis with a positive 1 and a negative 1. And then we know that we want to graph 2 periods of this function. So we're going to put a starting tick mark right here on the axis, and then 4 evenly spaced marks, 1, 2, 3, 4. That's going to be the end of our first period. And then I'm going to go ahead and do the next 4 tick marks. So 1, 2, 3, 4, and that's going to be the end of our second period. And we know that this is a sine function, so we remember that the pattern for the sine function is middle, high, middle, low, middle. So let's go ahead and place our dots. Middle, high, middle, low, middle. And that, of course, is the end of the first period. And then let's go ahead and do the dots for the second period. We've already got the first dot in the pattern, so we've already got middle. And then the rest of the pattern is high, middle, low, middle. And we can go ahead and connect our dots. Remember, you want a nice rounded shape at the top and bottom of the wave. And the last thing we're going to do is calculate the horizontal axis labels for the end of each cycle. So remember, we saw before that the way to calculate the labels for the end of each cycle is to say starting point plus period equals ending point. So for this first cycle right here, we are starting at 0, and then the period we know is 2 pi over 3. So right here we have 1 period of the graph, and so from here to here is 1 period. That's 2 pi over 3 radians. So if we start at 0 and we travel 2 pi over 3 radians, where do we end? Well, it's obvious this time because the calculation is really easy, but let's go ahead and write it down because we want to start a good habit. So to calculate the end of the first cycle, we put our starting position, which is 0, plus our period, which is 2 pi over 3, And that means that this period ends at 2 pi over 3. So we need to put that label there. And now for the second cycle, it also covers 2 pi over 3 radians. So if we start at 2 pi over 3 and we travel 2 pi over 3 radians, then 2 pi over 3 plus 2 pi over 3 more is 4 pi over 3, and that's the label that goes at the end of the second period. So it's very important that for every graph that you have your vertical axis labeled. You want the highest point and lowest point on the graph to show on your vertical axis, and you want the beginning and end of each period labeled. Now we kind of get a pass on the beginning of this first cycle because it's clearly at the origin, so it's clearly 0. But the end of each cycle, it's important that we have those labeled. So again, anytime you have to do calculations for horizontal axis labels, you will always calculate your starting point plus your period to get your ending point. And as I said before, in this section of the textbook, all the patterns begin at x equals 0, which is the y-axis. But in section 4.2, we'll learn how to do horizontal shifts to our graphs, and then the starting point can be something other than x equals 0. So we will get to a place where our first cycle does not start at the origin, but for right now in this section it does. Let's get another example. So this is example 6, and it says graph 2 periods of y equals the cosine of 2x over 3. Label the highest and lowest points on the y-axis, and label the end of each cycle on the x-axis. So let's start off by analyzing our A number and our B number. So you can see here that the A number, which is the coefficient of the function, the A number is 1 because we don't see it there, so A is 1. And the B number is 2/3 because the B number is the coefficient of the variable. Now we know that amplitude is the absolute value of A. And so A is 1, that means amplitude is 1. And since A was positive, that means there's no flip happening here. So you remember from before that if A were negative, it would cause the graph to flip over the x-axis. But in this case, A was positive, so no flip. All right, now this is a cosine function, and we know that the pattern for cosine is high, middle, low, middle, high. And then period is 2 pi over b. So in this case, that's 2 pi over 2/3. Now you know how to divide by a fraction. Dividing by a fraction means multiplying by the reciprocal of that fraction. So 2 pi divided by 2/3 is the same as 2 pi times 3 over 2. In this case, we would now have a 2 in both the top and the bottom, so they would divide out, and we're left with pi times 3, which we will write as 3 pi. So the period for this function is going to be 3 pi. Now, you can do things in any order you like. You could choose to go ahead and graph your function at this point. I'm going to go ahead and calculate the labels that go at the end of each cycle. So we know that this graph is going to start at 0. And we also know that the end of each cycle is calculated by saying starting point plus period gives us ending point. So if this graph starts at 0, our starting point is 0, plus our period, which is 3 pi, that's going to give us 3 pi as the end of the first cycle. And then if the first cycle ends at 3 pi, that's where the second cycle begins. So for the end of the second cycle, I start at 3 pi, I add another period, and that adds up to 6 pi. So the second cycle will end at 6 pi. Okay, now let's start our graph. First, let's get the vertical axis. So we know amplitude is 1. We're going to need our vertical axis labeled with a positive 1 and a negative 1. And then let's lay out our tick marks. So we're going to have a starting tick mark at the origin, and then 4 more tick marks. And that's going to be the end of our first period. So the label that goes here is 3 pi, and then 4 more tick marks, and that's the end of the second period, so the label that goes here is 6 pi. Now let's plot the dots for the pattern So we get high, middle, low, middle, high. That's the first period, and then we repeat that for the second period. And since the pattern for cosine ends with a high, we know that the last dot we plot should be in the high position. Now we can go ahead and smoothly connect our dots to get our graph, and that's it. We're done. This is the graph of 2 periods of cosine of 2x over 3. Now the best way to get good at graphing is just to do lots of graphing. So we're going to do a few more examples together. Here is example 7. It says graph 2 periods of y equals -2 sine of 3x, and then the standard reminder about the labels on the axes. So the first thing we want to do is figure out what the a and b numbers are. You know that a is the coefficient of the function, so a is -2, and b is the coefficient of the variable, so b is 3. Now the amplitude is the absolute value of a, so amplitude is 2. And because a is negative, there's going to be a flip over the horizontal axis. This is a sine function, so normally the pattern would be middle, high, middle, low, middle, but because of the flip, we're going to say the pattern is middle, low, middle, high, middle. And then we know period is 2 pi over b, so period in this case is 2 pi over 3. Let's go ahead and calculate the labels for the end of each cycle. We know that the first cycle begins at 0, and then if we add 2 pi over 3 to that, we will end the first cycle at 2 pi over 3. And then the second cycle starts at 2 pi over 3, and if we add another period to that, then 2 pi over 3 plus 2 pi over 3 is 4 pi over 3, and that's where the second cycle will end. Now let's go ahead and label the axes of our coordinate system. So amplitude is 2, so we know we're going to have labels of +2 and -2 on the vertical axis. And then for the horizontal axis, we know we put our starting tick mark at the origin, and then we lay out 4 more tick marks. This is where the first period will end, so the label that goes here is 2 pi over 3. And then for the second period, we put 4 more tick marks, and this is where the second period will end, so that label is 4 pi over 3. And then let's put the dots for our pattern. So it's middle, low, middle, high, middle, and then repeat. We've already got middle, so then the next dot is low, then middle, high, middle. And let's connect our dots with that smooth curve, rounded at the bottom and rounded at the top. So here we go. And that's it. Here we have 2 periods of y equals -2 sine of 3x. Now it can sometimes happen that the number in the b position is a multiple of pi. When that happens, it looks like it's going to make the function harder to graph, but it's actually not any harder at all. All that happens is that the x-intercepts and the labels on your horizontal axis will now be rational numbers. So here is example 8. It says graph 2 periods of y equals -3 cosine of pi x. Now you see what I mean about it looking harder? Because we're used to seeing a whole number here, when you see a pi symbol here, it can throw you off just for a minute. But don't let it throw you off. Just know that everything's going to work out fine. So first let's look for our a and b numbers. So we know that a is going to be -3, and in this case b is pi. Okay, so that means that the amplitude for this function is +3. You know amplitude's always positive, but the negative on our a does mean that the graph will be flipped over the horizontal axis. Now the pattern for cosine is high, middle, low, middle, high, but we have a -a, so with the flip, it's going to be low, middle, high, middle, low. And now let's do the period. Period we know is 2 pi over b. So in this case that's 2 pi over pi. And what happens is the pi's divide out and we see that the period is 2. Okay, now to calculate the labels that go at the end of each cycle, we know that the first cycle starts at 0 and then we're going to add a period to that. So obviously 0 plus 2 is 2. So this will be the label that goes at the end of the first cycle. And then the second cycle starts at 2, and when we add a period to that, we can see that the second cycle ends at 4. Okay, now let's set up our axes. So the amplitude is 3. So we're going to have positive 3 and negative 3 on our vertical axis. And then for the tick marks on the horizontal axis, we know we put one tick mark at the origin, and then we go 1, 2, 3, 4. Here's the end of the first cycle, and so the label that goes here is a 2. And then 1, 2, 3, 4, this is the end of the second cycle, and so the label that goes here is 4. Now we'll place our dots, so it's going to be low, middle, high, middle, low, and then continue that pattern. And now we're ready to connect the dots. Now remember that we can't just go straight from dot to dot. There's nothing straight on the sine function or the cosine function. So when you connect your dots, make sure that you come out a little bit so you can show that you're coming out of that valley. And then as you go toward the top, remember, just let it gently slope as you reach the top of the pattern, and then gently slope down so you get that hilltop shape. And then just continue until you've completed both cycles. And so here's our finished graph of y equals negative 3 cosine of pi x. I hope you see how important the labels on the axes are to making the graph match the function. Without the labels, we wouldn't know what function is being graphed. So the labels are super important. They're not a little extra detail. They are really an important part of what makes the graph correct. Okay, now that we've graphed several functions, let's kind of go backwards. Now we're going to look at a graph and see if we can figure out the equation that created that graph. So what we have to remember here is that because b controls the period, it also controls how many cycles fit between 0 and 2 pi. You may have already noticed this. If b equals 1, then one cycle fits between 0 and 2 pi. But if b equals 2, then 2 cycles or 2 periods fit between 0 and 2 pi. So the b number tells you how many complete periods you can expect to see between 0 and 2 pi. And we saw a couple of these graphs when we first started thinking about period, but let's look at them again. So our focus here is from 0 to 2 pi. Notice that here we have the sine of 1/2 x. So b is 1/2. So we would expect to see half of a period between 0 and 2 pi. And that is exactly what we see here. Here is the graph of y equals sine of x. And of course here b is 1. So we should see one complete cycle between 0 and 2 pi. And look, we do see that. Middle, high, middle, low, middle. So one full period between 0 and 2 pi. Here's the graph of sine of 2x. And so if we find the 0 and the 2 pi, I think we can see two complete periods between 0 and 2 pi. And here is the graph of y equals sine of 3x. So how many cycles do we expect to see between 0 and 2 pi? Well, in this case, we expect to see 3 cycles. So let's look at the graph. Here we have 0 and 2 pi, and let's count how many cycles. Middle, high, middle, low, middle, that's 1. And then middle, high, middle, low, middle, that's 2. And then middle, high, middle, low, middle, that's 3. So we have 3 complete cycles between 0 and 2 pi. Okay, so here's example 9. And it says determine an equation of the form a cosine bx or a sine bx, where b is positive, because remember I told you we would never have to worry about a negative b, for the given graph. Okay, so the first thing I want to look at is the shape. I see here that the shape is low, middle, high, middle, low. And that looks like an upside down cosine graph. And you can see from the center to the highest point on the graph, is 2. So it looks like we have an amplitude of 2, but because the graph is upside down, we now know that little a will be negative 2. Okay, let's count how many periods we see between 0 and 2 pi. Well, we can't fit a whole pattern between 0 and 2 pi, but it looks like half of a pattern. So we have half of a period between 0 and 2 pi. That means b is 1/2. And so now we just need to write the function with a and b in their proper place. And since this is a cosine function, we will have a cosine bx, where a is negative 2, and then b is 1/2. So it would look like negative 2 cosine of 1/2 x, or another way to write it is instead of writing 1/2 x, you could write x over 2. So you could say negative 2 cosine of x over 2. Let's look at example 10 together. So again, it says determine an equation of the form y equals a cosine bx or y equals a sine bx, where b is positive, for the given graph. Okay, I don't have all the blanks this time because I want you to learn how to analyze it on your own. So what was the first thing we looked at last time? Well, I believe it was shape. So let's think about the shape of this function. Middle, low, middle, high, middle. That's like a sine function, but it's upside down. So we can see from this that the amplitude is 2, but because the graph is upside down, we know that a is going to need to be negative 2. And now let's count how many periods we see between 0 and 2 pi. Well, we have 1, 2 complete periods, so b is 2. And now when we write our function in this form, we'll write y equals negative 2 sine of 2x. Let's look at 10b. So again, we're determining the equation of this graph, and it has one of these two forms. So first, let's think about the shape. It looks like our shape is high, middle, low, and then it cuts off, but that is enough for us to know that this is a cosine shape. And you can also see that from the center to the highest point is 3, so that tells us that the amplitude is 3, which means that a is 3. And now let's think about how many periods we see between 0 and 2 pi. Well, we only see half of a period. So we got the high, middle, low, but we didn't get the rest of the shape. So it looks like half of a period, and so b is 1/2. So when we write our function, we'll write y equals a, which is 3, cosine of bx, but b is 1/2, so 1/2 x. Or again, you could say 3 cosine of x over 2. Those are equivalent. And our last graph. So again, we are determining an equation for this graph. And so we want to start by looking at the shape. And it looks like low, middle, high, middle, low, which is an upside down cosine shape. And we can see that the amplitude is 3. And the upside down shape combined with the amplitude tells us that little a is negative 3. And now we want to count how many periods there are between 0 and 2 pi. So low, middle, high, middle, low, that's 1, 2, 3, 4. So 4 periods there means that b is 4. And so when we write our function, we will write y equals a, which is negative 3, cosine of 4x. Now that's it. Now graphing is a skill that takes time to learn. So what I want you to do is not just your MyLab homework, because that will only help you practice calculating these numbers and calculating the period, etc. But what you really need to do is practice drawing your own graphs. And MyLab cannot grade graphs that you drew, because obviously if you're drawing graphs on paper, MyLab can't help you assess that. So what I want you to do is go to Canvas, find the textbook problems that I have put there for you, and draw your own graphs by hand. And then compare your hand-drawn graphs to my hand-drawn graphs that you will see in Canvas. And that's how you'll know if you're graphing correctly or not. If you have any questions about whether you're graphing correctly or not, if you're in my traditional class, you can come to me. You can email me a picture of your work. Or if you are taking trigonometry online, you can email a picture of your graphs to your instructor, and they will be glad to look at them for you. But it's really important that you practice drawing your own graphs by hand, and let us give you feedback if you need it. Okay, so good luck. I'll see you guys again in section 4.2.